in this lecture, we're going to be talking about the gyroscope, which is used to measure our rotational velocities. So let's go ahead and get started. So here's a depiction of a MEMS rate gyro. And the gyros are really interesting contraption. What we're going to do is we're going to excite movement, velocity in this direction. So we have our mass suspended, and this is something that we do. We excite the mass by moving it up and down. And then we allow our mass to feel the rotation about just a single axis. And again, so this axis is going to be coming straight out, basically straight out of what's depicted there as a wall. And then any point experiencing rotation, and well, since we're exciting it, so the mass has a certain given velocity where it's moving up and down according to this picture. That's going to, this rotation is going to cause what's known as the Coriolis acceleration. So, and that's given by the cross product. So now we have going up in one direction, the axis of rotation is pointing straight out. So those two are orthogonal. So if you cross the rotation into the velocity, you get the acceleration coming out the side. So this right here is our Coriolis acceleration. Okay, so we have our Coriolis acceleration, and this is a function of something that's unknown and something that's known. And this is what we're going to end up measuring. Okay. And in fact, we'll come down here. We generate the movement of the of the gyro up and down according to some resonating frequency. And so we know how it's moving. And we come down here, and we're going to be measuring a voltage, which is going to be some constant times the magnitude of this acceleration. And again, this acceleration is just moving in a single axis. And so we'll come through, and you'll end up designing 3 different axes, or having 3 different apparatuses to measure all 3 different axes. Now there are a couple typos. This one is not true. It's omega cross V is equal to omega V. And that's because we know the axis. So the angular rate of rotation about a sensitive axis of the gyro and V are orthogonal. That gives us that relationship. But at the end of the day, the most important aspect to get from this slide is that the voltage of this gyro is going to be proportional to the rotation. So it's proportional to the rotational velocity. Okay, which is really awesome. So now, again, it's like the accelerometers where we're just measuring a voltage of coming in, and this voltage is proportional to the thing that we're trying to measure. So again, here's a picture of a gyro, and we can rotate in one direction. So that's coming out of the screen, right? Actuation going to the left or to the right, and we're going to measure the Coriolis going up or down on our screen. So a pretty cool little apparatus. Then we jump into actually generating the model, right? So here, again, this is a voltage. This is our angular velocity. Then we have a bias term. And so again, biases are slowly varying or nearly constant parameters. And so you measure it typically every time you start. You try to get that bias, or you can include it into your common filter to be trying to estimate that bias. And then we have something that's given by white noise. And we'll say that that's typically zero mean. If it's not zero mean, we'll put the non-zero component into the bias. So we have units of voltage. We're converting, again, that K gyro converts from it's a gain that converts from our angular velocity to a voltage, and then we have these biases. So when we model it, we come in and we just model it as our P, Q, and R, right? So these are just our rotational velocities. And we'll also just model it as some bias. So again, we're going to assume it's constant over the time that we care about. And then we have our white noise. And so we can generate that signal rather easily. We just take our rotational velocities and add the noise terms to it. There you go. Now we have a bias sensor model.